that you fall over, we're fine. You gonna do a live demo or something? All right. Can we have some silence back there, please?
Yes.
Thank you.
Hello, I'm excited to be here today. My name is John Paul Arroyo. This is my partner, Eddie Escobar. We're going to be discussing friction analysis between reinforced fibers and the machines we made to test this. So we wanted to, like I said, we wanted to test the coefficient of friction between reinforced fibers. The testing method we were using is something called the twisted strand method. As you see here, there's an apparatus here using the twisted strand method. That you're using a dead weight here with a pulley, and this is where the name of the twisted strand method comes from, is where you have a yarn helix right here, and this is where the friction is analyzed. It goes up through the pulley here, and the tension is measured right here, and it comes back down to a motor where it pulls in the yarn. So this is the STeam standard. As what was before, there's the yarn package, the guide. It goes through an adjustable input tension, through a tension gauge, where it'll read the input tension down to the yarn helix. This is where we'll be analyzing friction, to the output tension, and to the yarn take-up. To measure the coefficient of friction, we will be using this equation. But in order to use this equation, we have to know what the input tension is and the output tension. The zero twist tension is the tension without any friction occurring, where you just put the fiber through the pulleys without using the twisted strand, or making the twisted strand. The number of wraps we will be using for the twisted strand is going to be 2.5, because that's what was recommended by the STeam standard. And we also have the apex angle. Next slide. So we believe that we can improve the current STeam standard that was given to us by many different ways. First is reducing the size of the test into reducing the size and making it more mobile, because the apparatus you saw before was very large, so you can walk around with it. Also, if you reduce the size, it would have potential for SEM imaging. We believe that we want to incorporate the SEM imaging within the twisted strand method, because when you as the test is occurring, we like to have a visualization on the microscopic scale to see where these fibers may fail and where the friction is occurring, and it'll give us more consistent results. It'll also be in a vacuum in the SEM, because that's helpful as well, because when this test is run, there are certain factors that play into the changing in friction, like temperature and humidity. So you have more consistent results to compare with other researchers or other people across the country, because you're working with the same controlled environment. Next slide. So this is the proposed design that we showed you in Senior 1 that I made in SolidWorks, where we had one pulley. This would be the yarn package. The yarn package would go through the bottom pulley, create the helix down here, go through one tension gauge for the input tension, back down up to the, from the input tension, the yarn helix back up to the output tension gauge, and this would be the yarn take-up. Next slide.
I'm going to be talking a little about the components that we actually ended up choosing for our specific prototype. We have two different controllers here. One is to control this little aluminum servo arm, which is going to be able to adjust the input tension going into the first tension gauge. This other controller is to regulate the speed of the second spool that is collecting the yarn, so we can adjust, we can have it go at nearly zero speed, or we can move it up to make it a little faster if we wish. For the input tension itself, we decided to use a servo motor with an aluminum arm, on top of which there is a pulley so that the yarn can pass through. And for the spool that is motorized, we're going to use this motor with a little pinion and a gear system in order to. Other than that, it's just some basic screws and pulleys that we use to fasten the box together and affix the pulleys onto the top surface of the box that we'll show in a second. We did end up modifying our design. As you can see, there's a difference between this model right here and what we are going to show you. For one, the spools that we have selected, instead of having them on top and increasing the total width of the box, we decided to place it underneath and inside. That way it looks all cleaner and you have more space. You can make the spools bigger, you can allow for more yarn so you can test more with less interruption. We also included this little slot right here in order to be able to change the angle, because as you saw in the earlier formula, one of the parameters that you needed to use was the apex angle, which was the angle at which the helix interacted between this line right here. This is a cost analysis based on the components that we have selected for our prototype. Everything from the first original sheet of metal that we purchased all the way down to the screws and everything we put. We also included a total manufacturing-wise of 23 hours. I know it might sound like a small number in total, but this is purely just to put the device together. And as a total cost, we have arrived at around $700, which in the first semester we estimated to be between $500 and $600, so it's not terribly far off. Next slide. This was a breakdown of all of the hours spent on the manufacturing thing, every single process that had to be done, the number of hours put into it, and then finally, assuming a cost of labor of $15 an hour, we came up with $345 for labor. If you want to reduce this cost, obviously it's very simple to do. I'm not an experienced machinist, but I'm sure that there are ways to either buy pre-assembled components or be able to manufacture things quicker. But I will be talking a little bit about the manufacturing process since we did design everything from the ground up. As I said earlier, we did originally buy a 1 square foot sheet of 1/4-inch thick aluminum. We put it through a metal cutting bandsaw to cut it roughly into the sizes that we wanted to, and then we used a mill to get it down to the exact size that we wanted to. We used the grinder to smooth out some of the edges, and there's assorted hand tools here like a caliper to measure that everything is according to the sizes that we wanted, which were given to us originally in the design objectives. Once all the plates were done, we drilled in some holes, we threaded some holes, and one of the challenges that we eventually found was that our motor was a little too thick, so we had to end up milling a pocket into one of the plates in order for it to fit. Just one of our several challenges that we had to come across along the way. That's the machine drilling the pocket so we can fill in the motor. Also, we did want to manufacture our own components. We know it's not exactly the most cost-effective or time-efficient. However, since it is a design project, we wanted to be able to design our own components. So what we did use was a lathe to make this little component onto which we would later assemble a spool. And that's where the yarn is and where it would be taken up. Our final design, which we brought in today, is just like this. We have a couple of spools up here in order to guide the wire, all as we have explained before. We have this aluminum servo arm right here to be able to swing back and forth in about a up to 90 degrees, so we can adjust the input tension as we please. And this slot right here to move this particular pulley up so we can adjust that angle if we wanted to. On the interior, like I said, we have one servo arm here controlling this pulley. We have one spool that has the material and one that is going to be consistently moving to pick up the material from this spool. Our final dimensions were approximately 6.5 inches by 4.7 inches by 2 1/4 inches. It weighs approximately 3 pounds. The input tension arm can swivel up to about 90 degrees. That apex angle right here to about 30 degrees. It can be moved up to approximately 60 degrees. And as far as the motor take-up speed, it can be adjusted anywhere between almost nothing and 1/2 inch per second. Before we get into that, I just wanted to show you guys a live demonstration again, I said there's these two blocks. One is controlling this input tension. I don't know if the people in the back can see, but you're more than welcome to come see. This first controller is supposed to move this arm. So if we wanted to design, if we wanted to increase or decrease that tension, we would be able to do so. And the second one is responsible for actually moving the motor. We could have it running fast, or we can slow it down. Eddie, let's go. It might be a little difficult to see, but it's working. It could be used for a bunch of different materials, but for time and cost reasons, we just made this out of dental floss so you guys can actually see it working. Now, since we do not have the actual tension gauges with us, we'll explain that in a moment, we decided just to run some numbers just to give you an idea of the things that we could do. Ideally, we would like to have two tension gauges, one at the input and one at the output, so you can measure the two tensions and thereby be able to find the coefficient of friction, or knowing the coefficient of friction, you can use one of the tensions to find the second. The whole purpose of this is to be able to experiment with it and be able to determine from some of the parameters one of the other parameters. There is obviously much room for improvement. We have to make this machine lighter. It might be a little too heavy to use for SEM imaging. The chamber is very delicate, and we do not want to damage a piece of equipment that is valued at over $500,000. So future designs would include to make that more lightweight. We can probably use 1/8 of an inch aluminum sheets instead of a 1/4 inch thick, which accounts for much of the material. Another thing that we're going to eventually add into this is to conduct more research on the tension gauges. Because tension gauges, as we have researched, there are some that do our job, that do what we wanted to do. However, it was very expensive, and due to financial constraints, we could not purchase those components. However, we did want to design the machine so that should someone purchase those components, you could just put them right there, and you can test. And finally, vacuum compatibility. We are not 100% sure on the components for this particular material, whether they can work under vacuum conditions. We did attempt to contact the manufacturer, and they were unclear. But we did end up choosing these components specifically for cost purposes. We did end up just building a prototype, and we had plans on making future models. This is just an example of one of the tension gauges that we did look at. It does everything we needed to do. It is the EMTX limited access digital tension meter, which can measure between 0.5 and 500 centinewtons or grams. This little width right here is 1 inch, which we have allotted more than enough space to be able to stick in there. And as you can see, the base price is anywhere between $1,900 and $2,000, which, since we did not have any funding for this project, was a little out of our reach. There are also vacuum compatible motors out there, so we just wanted to have you guys aware of that. But again, due to time and financial constraints, we just ended up choosing cheaper components for a base model so we can show you something that actually works.
So for the global learning aspect of this design, or for this project, the applications and the uses of these experiments, understanding friction between fibers, can be applied to, say, ballistic vests and body armor as well. Understanding the friction, and surface coating can help improve the performance of, say, a ballistic vest or some kind of or a fabric, and can basically improve the performance of it. So I think this kind of this research is interesting, and I think it'd be very beneficial. This test would be very beneficial to understanding more about the model of the fiber you are analyzing. And as well, improve the quality of clothing, athletic gear, for the next slide. And that's about it. And we're done.
Okay.
And
Well, before we take questions, there are a couple of special thank yous that we want to if our advisor, Dr. Benjamin Basil, is in the room here today with us, as well as another person who has been very beneficial to our manufacturing process, Mr. Rick Zigarelli, who is also there as well.
All right, questions?
Would you sell this to a textile company? Is that where something like this would be used?
It can be, but it's more for a research institution. So more people that are interested in materials engineering would want to see how these fibers interact and conduct experiments based on certain coatings, how it affects friction. But yeah, you can definitely sell it to a textile company if they want to be able to test their own materials.
I think a parachute guy would be real interested in this.
Can you talk about changes that you would make to the design in the future?
Well, all throughout our design, there have been multiple changes. There have been many different changes ever since we started. Obviously, the first change, as we mentioned earlier, this, I know you guys haven't picked it up, but it's pretty heavy. Let me disconnect everything just to make it simpler. This machine is pretty heavy.
How heavy?
Well, we mentioned it was approximately 3 pounds. But still, it's not something that we wanted to try to put inside of the SEM. We don't want to damage that piece of equipment. It's very expensive. So future improvements, definitely start making this more lightweight, make it thinner. Possibly we can even remove these side plates over here, just make it stand on 4 pegs here in the corners, so you can actually have a visual inside as well, and it's, you can reach in more easily. As far as actually perfecting the design, we talked about wanting to create vacuum compatible, well, not create, purchase vacuum compatible components once we are allotted a bigger budget. And yes.
Any other questions? No. We're hearing none. Thank you so very much. And the last